Last week, we learned several equations that will take us through our study of kinematics. When we started our study of kinematics, we started it by looking at graphs, and what we're going to do today is take those equations that we got from our graphs last week and learn how to use them. So kinematics is known as the science of describing motion using equations, diagrams, and graphs. We've already done quite a bit with the diagrams and the graphs, and now we're headed towards the equations. Most of what we're talking about today will be review. You will see the equations that we learned on Thursday last week again, and you'll see how to use them. Remember from before that velocity is the rate of change of position. So in other words, velocity is distance divided by time. How quickly is your distance or your position changing? You can use this equation when you are finding average velocity or when you're traveling at constant velocity. Those are the only times that you can use this equation. If you have any acceleration or deceleration going on, you have to use a different equation. Remember that velocity is typically given in meters per second, distance is typically given in meters, and time is typically given in seconds. That can vary from problem to problem, so read carefully. After we learned about velocity, then we learned about acceleration. Acceleration is the rate of change of velocity. So how quickly is your velocity changing? The equation that we just learned for acceleration is equal to the final velocity minus the initial velocity divided by time. Remember that acceleration is typically given in meters per second squared. Velocities are both typically given in meters per second, and time in seconds. And again, that can change depending on what problem you're doing, so read carefully. Remember that a positive acceleration generally means your object is speeding up, and a negative acceleration means you're slowing down. On Thursday, we took some of those graphs and we transferred them into equations. These equations are known as Galileo's equations because he was partially responsible for developing them. They are used to relate velocity, acceleration, distance, and time. So those are the four variables that you will see in these equations. When we learned these equations on Thursday last week, we learned 5, but 2 of them were exactly the same, just rearranged, solved for something else. So there's really only 4 different equations. The first one, final velocity equals initial velocity plus acceleration times time. The second one, final velocity squared equals initial velocity squared plus 2 times acceleration times distance. The third one, distance equals 1/2 the quantity of final velocity plus initial velocity times time. And the fourth one, distance equals initial velocity times time plus 1/2 acceleration times time squared. All of these assume constant acceleration, and that is something that we have assumed since we started our study of kinematics, that if there is acceleration, it does not change, that the acceleration itself remains constant. This is not to be confused with velocity, which does change when you have acceleration. Let's do a couple of examples, and then you'll be free to get started on your problems. You travel to the supermarket 1.5 kilometers away in 10 minutes. What was your average velocity? Because the question is asking for average velocity, I can use the very first equation we learned, and I need to pay attention to the units in this problem because they are not the standard ones that we're used to. We have distance equals 1.5, time equals 10, velocity equals distance divided by time. So our velocity is equal to 0.15 kilometers per minute. Pretty simple. Let's do another example. Your car accelerates from rest to 35 meters per second over a course of 150 meters. How long does it take you to do this, and what is your acceleration? Look at what you're given. Your car accelerates from rest. What does that mean? Accelerates from rest. Accelerates from a stop. So your initial velocity in this case is 0. And your final velocity, 35. And distance, 150. How long does it take you to do this? We're looking for time. And what is your acceleration? We also need to find A. There are multiple ways to solve this problem. You have 4 equations to choose from, and you can decide if you want to solve for time or acceleration first. Depending on which one you solve for first, that can change the equation that you use to solve for the second one. As long as you get to the end point correctly, it doesn't matter which method you choose to solve this problem. Here's the one that I chose. Solving for time first. Distance is 150, final velocity is 35, initial velocity is 0. 150 equals 17.5 after we take the 1/2 times the 35. Time equals 8.57 seconds. To solve for acceleration, I could go ahead and use the time if I wanted to, but that time is a rounded number off the calculator. So my answer will be more exact if I go back to the information that was given to me in the question. Now, it's not wrong to go ahead and use that 8.57, and sometimes you'll have to. But if you can go back, it's not a bad idea to start over with the exact numbers you were already given. So I'm going to choose VF squared equals VO squared plus 2AD. Final velocity squared equals initial velocity squared plus 2 times acceleration times distance. I get 1225 equals 300A, and my acceleration is 4.08 meters per second squared. It's a positive number. Positive acceleration means I'm speeding up. And that's it for the notes. You'll have quite a few problems to practice with over the next day and a half. You've got one worksheet to start today. You will finish that tomorrow, as well as get a second worksheet tomorrow that the goal is to turn in by the end of class. So use your time and plan accordingly. The key is out on the front desk so you can check your answers as you go. Help each other along, and good luck. See you Wednesday.